Personally, I think these next two chapters are kind of
easy.
I think there's not going to be much more to learn in chapter 11. Chapter 11 is going to go by really quick. Chapter 11 is pretty much the next logical step from where you guys have been. What we've done so far is, all I've given you guys is, my board turned on? She didn't like it when I pressed that. Okay. What I've given you guys so far is one sample. Or one proportion. And that's good, and you guys have seen how we've applied that and we've used it. We basically compared it against hypothesized. I think the class average was this. Is there evidence to say it's not that? Right? That makes sense kind of where we've been. The next step, and this is probably, like I said, a little bit more valuable, is we're going to start comparing, instead of one sample against something that's hypothesized, we're going to compare two samples against each other, or two proportions against each other. And here's what that means. And we're going to look at actually data from my class. I might even pull up, never mind. We're going to look at data from my class last year to this year. Two different samples. I want to know, this year in Algebra 2, you guys all remember logarithms from Algebra 2, right? Love them, right? So what happens is this year in Algebra 2, we taught logarithms a different way than we taught logarithms in the past. Okay? So now me as a stats teacher, I want to see, is there evidence that today, the way we taught it this time, is better than the way we taught it last time? Does that make sense? This is now gets what's into, this should tie into, for those of you guys who are using these things in science, what you're doing. Sample A compared to sample B. You're looking at now two different populations. You're looking at two different samples and comparing them against each other. Who's better? Is there evidence to say? For example, I might be able to, actually I can, we might do that a little bit later on. I'll pull the data from our last exam. And I'll split you into two populations, boys and girls. And we'll look at the mean and standard deviation from the boys, and we'll look at the mean and standard deviation from the girls. And I'm going to say, is there evidence that the boys are better than the girls? Or, conversely, is there evidence that girls are better than the boys? You see what I'm saying? We couldn't do that before. We didn't have that statistic to do before. Now, since we have two samples, we can kind of compare apples to apples. Does that make sense? Same thing that we're going to do with the proportions. Instead of one proportion against something hypothesized, we're going to take two proportions. For example, if I look at the proportion of A's of girls in this class to the proportion of A's for guys in this class, I would have a proportion for the guys. Agreed? Be like, I don't know. It might be like 2 out of maybe 15. For the proportion of A's for the girls might be something like 3 out of 17. Is there evidence to say that the proportion of A's for girls is greater than the proportion of A's for guys? That's a 2 proportion z-test now. Does that make sense? Still everything's the same 8 steps like it is before. Still, everything is the same. Check for independent, random, and what? Normality. Same 3. So, like I said, is it easier? I don't know that it's easier. It's really kind of more of the same. So, the hardest thing in this chapter, chapter 11, is when to use what test. Today we're looking at 2 independent samples. And as I said, naming your statistic is a big deal. 2 independent samples is what we're looking at today. That's talking about, say, 2 different populations. As I said, we're looking at boys and girls. In the case of the data that I have in just a second, it's going to be last year's Chapter 7 test to this year's Chapter 7 test. Last year's population was my populations of students last year. This population, my population of students this year. Those are 2 different, 2 independent populations. Does everybody hear what I'm talking about when I say independent and recognize that difference? Boys, girls, last year's students, this year's students. Because tomorrow, we're going to look at dependent samples. Okay? Dependent samples. And those are going to be samples where the population is the same or related in some way. Okay? So I'll look to kind of define that a little bit more as we look at tomorrow's. But today I want to really focus on the idea that this is a two-sample independent t-test. Two-sample independent t-test, we're looking at two different distinct populations there. Okay? All right. This is what it looks like. Here's your t-test. Here's what it looks like. As I said, you have two samples now, X bar 1 and X bar 2. You're going to be comparing it to a hypothesized difference. And I'll talk about the hypothesized difference before, or actually later. Before we had t, it was x bar minus mu over s of x over the square root of n. That was our old t-statistic for one sample. This is our t-statistic for two samples. We're talking about, like I said, two independent samples, comparing it to a hypothesized difference. Now, what we have to do when we have two samples is we've got to merge our standard deviations. So the denominator here is a little bit more complex than it was under our one sample. Because if you think about it, on our original one, we just had that deviation, agreed? Was there standard deviation from our sample? Okay. Now, in terms of kind of dealing with it for two samples, I have our deviation for sample 1 and our deviation for sample 2. So I need to combine all that spread. Does that make sense? I've got to make them work together because I'm combining them. I'm looking for a difference between them. So what we're going to do, and this is what's weird about standard deviations and variance. Variance, which is s squared, is unbiased. Okay, so you may see something like that. S squared is unbiased. So what we're going to do is we take our standard deviation and we square it to get it to the unbiased statistic. And then we divide it by n minus 1. That's the number of sample 1. And then we're going to square it divided by the number of our sample in sample 2. Then we're going to combine them, and then we're going to square root them. Okay? So again, what we're doing is we're trying to combine the deviations there. So we get one deviation. Students will think about subtracting these right here because we're subtracting up there. And that's not the case. We're not subtracting. You can't subtract randomness from randomness and make it less random. Right? It's still random. So we've got to combine it from both of our samples. That's about it. I will tell you, this is the only time you're going to see the equation for degrees of freedom in this class. Okay? This equation for degrees of freedom for a two-sample independent t is a mess. Okay? It's a big, messy calculator crunch. Don't worry about it. Okay? Do you agree if we had the standard deviation from sample 1 and the number of people in our sample, we could plug in these values into this equation and calculate the degrees of freedom? You guys agree with that? Okay. You don't have to do it. Your calculator will do it for you. The catch is your degrees of freedom need to be truncated. Now, truncated is a word that I haven't used a lot in this class. I don't think I've ever used it. Okay? Remember how degrees of freedom works on our T chart. 1 degrees of freedom is at the top, and then infinite degrees of freedom at the bottom. We said degrees of freedom, the more degrees of freedom you have, the more confidence you have, and the tighter and narrower that T distribution is. Agreed? Does everybody remember that general kind of description of the T distribution? Okay? So, truncated means to be cut off. And here's what I mean by that. Let's say you got something like 89.95 degrees of freedom. We would round that up to 90, wouldn't we? Does that make sense? But if we rounded that up to 90, wouldn't that be cheating my degrees of freedom a little bit? Because I don't technically have 90 degrees of freedom. And 90 degrees of freedom is more free. It's got a better distribution than 89 degrees of freedom. That makes sense? Which is better than 88, which is better than 87, which is better than 86. So the word truncated here means when I have some decimal at the end of my degrees of freedom, I ignore it. I have to use 89 degrees of freedom here. Truncate means to ignore the decimal part. Okay? Everything else in class we've kind of rounded, so just make sure that you guys are okay with that truncating decimal part. We clear on that? That's just for the two proportion. Otherwise, it's n minus 1. If it's in one sample, I got 100 samples, I'm using 99 degrees of freedom. Right? All right, here we go. Two methods were used to teach a high school algebra course. A sample of 75 scores was selected for method 1. A sample of 60 scores was selected for method 2. The summary results are given below. Method 1 had a sample mean of 85 with a sample standard deviation of 3. Method 2 had 83, a sample mean of 83, and a sample standard deviation of 2. Okay? This isn't my actual data. I'll pull up my actual data in a second. But I just want to kind of set us up for something that's pretty straightforward here. And now it says test whether method 1 was more successful than method 2 at the 1% significance level. Again, you're seeing hopefully something where we can kind of start to get statistical validity behind actual real-life data. Okay? Statistical validity behind actual real-life data, so that, let's say, if this was just me teaching the course, and I taught it one way versus the other, I'd want to know, what if just eyeballing it, do we agree that that's better than that? A sample average of 85 is better than a sample average of 83. We kind of agree with that. Okay, we know that just by eyeballing it. But here's my question, and this is what we might ask in the business world. Maybe let's not talk about teaching, let's talk about dollars. I made $85 here and $83 here, standard deviation of 2, standard deviation of 3. Now, if that's what I made, maybe method 1 takes me a lot longer to do. And method 2 takes me half the amount of time. Do I want to know if there's a statistically significant difference between those two? Yeah, it's valuable. Me as a teacher, maybe I got that result teaching it with a way that took me 3 hours every night at home. This way only takes me an hour at night every day. Does that make sense? If there's no difference between the two, let's put it this way. If there's no statistically significant difference between the two, why would I do that one? Unless it is better. Does that make sense? So, this applies to many, many things out there in the real world. This just happens to be the easy data set that I have. Same 8 steps. Is this blue hard for you guys to see? Are you guys okay with it? Okay. All right. We'll start with step 1. Step 1. Identify what it is we're talking about. We are looking at mu1 minus mu2, where that's going to represent the true mean difference, because we're looking to see if there's a difference between the methodologies. True mean difference between, what do we got here? Course 1 and course 2. Are you guys okay with me just calling it that? Okay. No, and I'll show you in just a second the hypothesis test part. So, yeah, I'll show you how that's going to look. So, step 1, true mean difference between course 1 and course 2. And I do want to talk about this for a second. Here's the way they're typically going to be. You're going to assume that there's no difference between them. Assume that there's no difference between them. In other words, mu1 minus mu2 equals 0. In this case, what did it ask? It asked us to find, test whether method 1 was more successful than method 2. We can eyeball that and say, yeah, it looks like it's better. But do we know for sure statistically? So we're looking for evidence to say that mu1 is better than mu2, right? How would I write that over here? That mu1 minus mu2. Do we agree that this is a one-tailed test? It doesn't say are they different, it just says I want to prove that one's greater than. So greater than. Mu1 greater than mu2. Greater than 0. Okay. And that's going to be less than or equal to 0. All right. Here's what helps visually a big time for students right now. And I think this will make it a lot easier to see how you write your null and your alternative hypothesis. Add mu2 to both sides of that inequality, and you'll get this. Mu1, that's lovely mu. Mu1 less than or equal to mu2. If I add it to both sides of that inequality, agree? And if I add mu2 to both sides of this inequality, mu1 greater than mu2. I hate that. Both sets are correct. I don't care which style you use, this style on the left or this style on the right. However, if you start with that, finish in that. If you start with that one, finish with that one. Keep them consistent. Does that make sense? Do you realize that they're saying the same thing? Yes.
Do you have to write that you assume that there's no difference? Or is that just because I assume?
That's step one. That's what we don't know what that is. Because the difference could be 2. Difference could be 5. Difference could be 7. Difference could be 0. This one could actually be higher. Because remember, I sampled, right? Does that make sense? So I sampled there, so I don't know, but I know out there is a true mean difference if I had every data piece. Okay, we're writing down null and alternative hypothesis. If it had said, is there evidence to say that number 2 is better? Then it would say mu1 is less than mu2 over here, and we'd fix it that way. If it said, is there evidence that there's a difference? Then if the word is a difference, that's a two-tailed test. We're looking at not equal to and equal to there. Just like before. Does that make sense?
So we always put that 0 there if we use the left.
If you use the left, you have to have this.
The 0.
If you use the right, you don't have to have that 0 because they're saying the same thing. But in terms of communicating understanding, remember I view what you write on paper, not what's in your head. You're communicating this on a AP exam or on your next exam. If you start with that and your second one's that, I don't know that you know that those are saying the same thing. All right. What significance level did it ask us to test it at? 1%. So 1% is alpha equal to what? 0.01. That's step 4. That's the easy one. Step 5. And you guys are a lot better at this than you used to be, which is good. Identify the test. This is a 2-sample independent t-test. We've got to really key on independent today. Need to key on the independent because tomorrow will be dependent, which is a matched or paired test, and it's different. All right? We have 2 samples. You need to justify random independent normal for both samples. Okay? I'll say it again. You need to justify random independent normal for both samples. So I'm going to go random. I think we have to assume random in this, right? I don't think it said. So we got to assume random. So I'll say assume both samples are random. Both samples are random. We also have to assume, what was my sample size in each of them, did it say?
1675.
1675. So I'll say what method 1 is n equals 75, and method 2 is n equals 60. I have to say, assume sample 1's population is greater than 750 students, and we have to assume sample 2's population is greater than, that just is what, 600, I think? 600 students. Both samples are sufficiently large. And I would cite that sample 1, n is equal to 75. Sample 2, n is equal to 60. And I'd say both are greater than or equal to 30. Therefore, central limit theorem applies. Random, independent, normal. Same three as they were before. Notice that it's just an extension of what we talked about before. And you guys can probably figure out where we're going. Step 6, write the statistic. It's a t statistic. It's a little bit different. X bar 1 minus x bar 2 minus mu1 minus mu2 over, this is a bigger one, s squared from sample 1, s squared from sample 2. Write it dry, then show it with your correct substitutions. Correct substitutions, we've got 85 minus 83 minus, we've hypothesized it to be 0 in this case, and I'll show you something about that in a second. And then standard deviations here, that should be 3 squared over 75 plus 2 squared over 60. Okay? Do we agree this is kind of more of the same? Yes, yes? I don't know, I'm out there. Yeah. We don't do it. We don't talk about it at all in this course. Don't. It's always going to be no. Yeah.
Can you go back?
Go back. Some of you guys already figure out we're going to calc next. Go to your calc. Yes, that's what we're looking for on this one. This is now a 2-sample t-test, so you need to find that. 2-sample t-test is number 4 on my calc.
And how do you know the sample was 75 and 60?
It says in the context of the problem.
Oh, okay.
It says you don't have, yeah, it says sample 75 is selected. No data on this, so we're going to go, let's see, X bar 1. Sample 1 had a mean of 85 with a standard deviation of 3. People in that one, there were 75 scores. And then sample 2 had a mean of 83. Standard deviation there was 2. There were 60 people in that one. Again, notice that your calculator will set it up in the not 0, 1, but which one's greater. We're looking for evidence that method 1, which is mu1, is greater than mu2. So highlight that one. Next thing you're going to see as you scroll down here, it says pooled, yes or no. For pooling in this class, always no. No, no, no. Just say no to the pool. It's winter. Don't go swimming. So, no to the pool. Always no pool. What's that? No, it has to do with how you combine your data. So, we don't do it. It's a different test.
Does TI do have pool in that?
I think so. I don't know. I didn't check and see if it has
Just
battery set. I know, grab somebody who has a TI. I think it has pool. They should have pool. All right, hit calculate. And we've got a T statistic of 4.6. Okay? And now look at the degrees of freedom. Notice that it gives you that decimal with the degrees of freedom. It's 129.08. What did I say about truncating? Okay. So our degrees of freedom is going to be what? 129. Our p-value, by the way, please don't report 4.414. That's 4.414 times 10 to the negative 6, which is pretty much what? 0. So report your t-value of 4.6291. So t equals 4.6291 with 129 degrees of freedom. It gives us a p-value of approximately nothing. We okay with that? Yeah, on your calc it does. It's df equals 129.08. Again, truncate that to 129.
So if it was 129.5,
No, truncate it, 129. Basically, truncate means forget about the decimal. Whatever number is there, forget about the decimal, cut it off. Because again, we've got to err on the side of this way, not this way. All right, from here, it's the same as it ever was. Step 7, p-value is less than or equal to their alpha value. We got 0 less than or equal to 0.01. That means we reject the null hypothesis. And with 99% confidence, we can say there is enough evidence to support the claim that method 1 is a better teaching method. Okay? Yeah, you probably should. Let me get that in there. I forgot that, so I apologize. We should, because I've seen them ding on it before. So yes, let me figure out how it fits well, though. With 99% confidence, we can say that there is enough evidence to support the claim that the true mean of method 1 is greater than the true mean of method 2. Let me reword that. True mean of method 1 is greater than that of method 2. There we go. And that's really restating our opponent hypothesis. That's better. Good question. All right. Not much new. You guys agree with that? Maybe the degrees of freedom, realizing that you've got to talk about both samples, but besides that, same as it ever was. You sure do look smart when you write these, though. Tell you what. Get to homework now? No. But what I'm going to do is I want you guys to do this. Okay? This is actual This is not on the notes. No, this is my actual data. I got to remember which one's what. Yeah, this is 2013, and this is 2012. Okay? This is the average on the log tests. This is actual computer output from those things. Notice that we get a lot of information that we haven't covered in this class. Well, count we've covered. That's the number sample. So I have 73 Algebra 2 students right now. All of last year I had 110 total. Because I have taught multiple sections. Right now I only have 2 sections. I'll have another section in the spring here. So I got n equals count we've got. N equals 73 and 110. So I'll highlight that. Max, min, and range. Max, min, and range. We've covered those things. Skewedness and kurtosis we haven't covered. We know how to recognize skewedness. The word kurtosis we don't talk about in this class. It actually has to do with the number on how skewed that graph is. Okay? So we do have some skewness in both of them. I'm not going to worry about that. We don't talk about that in this class. Standard deviation and variance. By the way, how do I go from my variance to my standard deviation? And how do I go from my standard deviation to my variance? Okay. So we've got those. We've seen those. Mode, which is our most common value. Median, which is the what? It's a percentile. What percentile is that? 50th percentile means 50% of my data is above it and 50% of my data is below it. So median we've got. Standard error, we'll talk about. We haven't really talked about that a lot. And then we have the mean. So what we're going to use for this problem, as you guys do your 8-step, there's my information. In 2013, this test happened to be out of 80. The test was out of 80. But in 2013, my mean from all 73 students was 59.2. We'll round it to 2 decimal places for you guys. 59.26. My standard deviation was 17.54 with a sample size of 73. In 2012, I had a mean of 61.37 with a standard deviation of 15.1 and a sample size of 110. Now I want you guys to do an 8-step hypothesis test and tell me if 2012 was better than 2013. Okay? Again, agreed that my mean is bigger in 2012, so I'd like you to prove, if you can, that 2012 was better than 2013. Make sense?
This is 2 points, right?
That's what we just did.